Okay, are there any questions? No? All right, tomorrow we're doing the KClO3 experiment. Actually, it's a KClO3 decomposition. It's a redox reaction in which KClO3 decomposes into KCl plus O2 gas. To balance this, we'll need 3 CAFs. KCl is a solid, and KClO3 is a solid. These are solid. Okay. When you look at KClO3, what chemical properties does KClO3 have? What are the chemical properties of KClO3? So this is soluble, all potassium salt. The solubility is typically thought of as a physical property, or just property. What properties does KClO3 have? That might be better. There's physical properties. It's soluble, potassium salt. It's a strong electrolyte, so it breaks up into ions. What ions does it break up into? That's in water. There's no water in this particular reaction, but we're dealing with these ions. The potassium ion is a chlorate ion. Okay, what else can you say about this? KClO3. You know, you want to have some kind of general feeling for the chemicals that we're working with in the lab. So do you have any general feeling for KClO3? You know? When you see something like KClO3, either a blank page comes up or you have some ideas of the properties. Well, that's good. It's soluble, it's a strong electrolyte, but what else? What else? Actually, we already did this. We did this before. I'm just reviewing. Maybe I did it too quickly. Maybe it's in your notes. Maybe it's not in your notes. Nobody remembers? Last week. Tuesday. Almost a week ago. Not quite a week ago. You know? Uh-huh. It's polar? All ionic compounds are polar. Because you got a positive pole, which is the potassium ion, and negative pole, which is the chlorate. Polar is just... Yeah, it's a strong oxidizer. The end conclusion from last week was, yeah, KClO3 is a strong oxidizer, and then to cap it off, we mixed it with a reducer. Do you remember what the reducer was? It was paper, but it wasn't that spectacular, so I mixed it with sugar instead. Do you remember that? Sugar and potassium chlorate. And so one of the things that stands out about potassium chlorate is it's a strong oxidizer. You could have figured that out by looking at what? If you looked at what, you could have gotten a clue that it's probably some dangerous stuff. What is that? The oxidation state on chlorine. Oxidation state on chlorine is +5, which is fairly high. It's losing 5 electrons is pretty high. Not as high as perchlorate. You know, the oxidation state in perchlorate's +7. apparently it's lost all its valence electrons. Do you think chlorine's very happy losing all 7 of its valence electrons? No. And so, do you recall the perchlorate explosion in Nevada? Showed the YouTube on. Remember that one? And then chlorate's only +5, which is a little better, you know, more stable. But is this stuff very stable? How's that reaction with sugar? No, it's not very stable. And so one thing that stands out about this is, wow, this looks like a strong oxidizer, right? But sometimes, you know, you lose sight of that because, you know, when we're looking at metathesis, do you remember going through the metathesis properties of this? You know, what ions does potassium precipitate out with? None, because all group 1 salts are soluble. Chlorates, right? Chlorates, we had the rule. Chlorates, acetates, and nitrates. Chlorates, acetates, and nitrates are all soluble. And so when you think about it, that's not going to precipitate out with anything. So do you guys remember going through the metathesis properties of potassium chlorate? I think we spent like 10 minutes going through it. Metathesis and acid base. Yes or no? Don't remember at all? Okay. All right. Well, that's a kind of analysis. You know, we looked at, you know, what will it precipitate out with anything? No. Are we going from stronger acid to weaker acid? No, we didn't call these, actually we called this one neutral, but we called this one a base. And so there's got to be an acid-base reaction, right? Chlorate is a base. How do I know? Oh, it's on the chart. Not this chart, but the chart, you know, posted on Piazza. Chlorate's a base. But if you say it's a base, then, you know, you got to give me an idea of, you know, how strong of a base is it? So do you remember me talking about this last time? Yeah, a little bit? Okay, good, a little bit, that's good. Because I use the analogy, you know, chlorate is about as good of a base as chloride. So you know what you should do? On your next acid-base titration, rather than using sodium hydroxide, you should use sodium chloride. And use sodium chloride solution to neutralize your acid. Is that a pretty good idea? Because chloride's a base. You know, I see chloride up on this chart. Over here. Do you see it? Chloride's a base. And so next time I do an acid-base titration, I'm going to ask you to use sodium chloride AQ rather than sodium hydroxide AQ. Good idea? Is it a good idea? No, it's a bad idea. It's a bad idea because what did I say about chloride? Its base properties? You know, somebody might say chloride's a weak base, but that's not really, that's being way too generous because it is so weak, we call it neutral. And so the same thing with chlorate. Chlorate's the conjugate base of a strong acid. Strong acids don't want a proton. This is what makes them strong electrolytes. The proton or the hydrogen ion breaks off easily. Why? Because the anion doesn't really have an attraction, a strong enough attraction, so water can easily disrupt that. And so we know that chlorates is in the same category of base as chloride. You aren't going to be neutralizing anything with it because it's essentially neutral. I guess repetition does help. Repetition does help, but you know, I'm running out of time, so I need to speed things up because I'm behind schedule. And so I'm not going to repeat myself as much. And so you got to try to catch it, you know, on the first round. And so potassium chlorate is a good oxidizer. That we know. But what if you know, what if you're in lab and it completely comes blank? You know, I don't know what chlorate is. It's just some chemical I need to mix, or some chemical we need for the reaction. Well, what you can do is you can look up this, and this is something I do more in Chem 1B, but I need to start doing this in Chem 1A. And that is, we go to the MSDS. Do you know what MSDS is? What it stands for? MSDS stands for material. Oops. What's wrong with this? Somebody's always fiddling around with it. Unfortunately, I don't know this well enough to fix it. Computer is selected. I was working this morning for my morning class. It's not working anymore. Shoot. Well, if things drop a complete blank, then you should, before we use the chemicals in the lab, this is part of proper prep, lab prep. This is something I'm going to start emphasizing more, especially since we had an accident in the morning class and people are coming very, very poorly prepared for lab, and just not really treating some of the chemicals that we use. They think, okay, since we're using this in lab, it must be safe. No. One of the things you do in chemistry is you learn how to safely handle dangerous chemicals. A dangerous chemical like this, KClO3, is a very dangerous chemical. KClO3 you wouldn't want to mix with what? You don't want to mix KClO3 with reducers, right? Otherwise you can have a potential explosion or fire. No, now it's working. It's just turning it off and on again. Did it? And so, if some of these chemicals, when you're going through the lab prep, and the chemical doesn't ring any kind of bell, you look at KClO3 and just blank page comes. You have no idea. But blank page doesn't mean it's safe. The blank page means you just don't know anything about the chemical. And so what you should do in cases like that where nothing rings a bell, you should go to the MSDS, Material Safety Data Sheet, and at least familiarize yourself with this particular reagent. And so we go down the MSDS and we see. MSDSs always have a 24-hour emergency line here. We call. There's some toxicological data. Potassium chlorate has an LD50, lethal dose 50% of the population, 1,870 milligrams per kilogram. So 1.87 grams per kilogram of body mass. So potassium chlorate is toxic, but you have to be careful about what toxic means. Every chemical. This is made by the chemical company. Every chemical company is going to tell you that their stuff is toxic, right? They're going to tell you, they're never going to say it's safe, because if they say it's safe and somebody has an accident, then they're going to be liable, right? And so everything, including water, water's toxic, right? Too much water, you can potentially drown, of course. Or nitrogen's toxic, because if all the nitrogen blows out all the air, and you're breathing nitrogen, there's no oxygen, so you're going to die. Right? And so people who work with compressed gases by nature are toxic, because if you have a compressed gas and the valve opens and blows all the air out of this room, then people die. And that's happened, And so everything's toxic. And so let's go to something like sea salt, which has a lot of potassium chloride, and see what the MSDS looks like for KCl. People eat KCl because they like the taste of, potassium chloride instead, but you look at the toxicological data for potassium chloride. Potassium chloride is toxic, right? The LD50 on potassium chloride is 2,500, so it's a little higher than the LD50 on potassium chlorate. You know, does that mean people don't eat? See, people eat this stuff. The people sprinkle this on their food, right? And so toxic, you have to use some additional analysis, you know, because every MSDS is going to say it's toxic, I think. And so, good luck. Unfortunately, these are animal tests here. But, that's it. Those are huge amounts. Then we look. Oops, the wrong one. Then we look here. You know, for acute health effects like skin contact, eye contact, etc., ingestion. Chronic effects, if you're working with this day in and day out, you know, and exposing yourself on a daily basis. This. Acute, they're usually large scale, but you know, skin inflammation, etc., burns, ulceration, any kind of strong oxidizer is damaging. Right? Air, you know, like geologists look back at least paleontologists look back in the history of the Earth and see, you know, oxygen rich, which is an oxidizing environment, versus an oxygen poor environment, and these cycles that happen. You know, as the amount of oxygen in the air increases, then lots of organisms die off. As the amount of oxygen decreases, then these anaerobic organisms come into play. And that happens, you know, underwater or above water or wherever. And so we look at these types of things here. And so you familiarize yourself with some of the hazards of these: eye contact, skin contact, etc. Some of the hazards, like chronic health effects, are like carcinogenic, you know, cancer-causing effects, not available. Mutagenic, you know, causing mutations, not available. Tetragenic, cause birth defects, not available. Developmental toxicity, not available. And so we're just cautious. We try to avoid contact with this stuff. Etc. Inhalation hazards. First aid. Okay, let's look at fire and explosion data. Flammable. Oh, it's non-flammable. Oh, this is safe. You know, we don't have to. Do we have to worry about fire? Non-flammable. Auto ignition. Temperature not applicable. Flashpoint not applicable. Flammable limits not applicable. Not applicable. Not applicable. Not available. Not available. Not available. Nothing. So it looks like it's okay, huh? Mechanical impact. Explosion, it looks like it's okay, right? So is this stuff safe from fires? No, because when we look at fires, we have to look at fires based on two things. We look based on the oxidizer. Is oxygen flammable? Will this room burst into flames if I light a match or a lighter? You know, there's 20% oxygen in this room. Won't we have a potential explosion? No, because when we look at flammability, we don't look at the oxidizer, we look at the reducer. And so, yes, of course, this is oxidizer. Small spill, large spills, handling and storage, exposure controls, physical and chemical properties. Well, here's some physical and chemical properties. This isn't very good because not available, not available. We got to look around at some others. But here, you know, out of all these not available, finally we get the incompatibility with various substances. Extremely reactive. So this stuff is extremely reactive. Yes, I tried to show it's extremely reactive. Or incompatible with reducing agents. Combustible materials, organic materials. And so these things are going to, you know, either catch on fire or explode, basically. So we have to be careful. We wouldn't want to mix potassium chlorate with sugar, would we? The sugar is a organic combustible material. How about chloroform? Oops. Potassium chlorate is a strong oxidizer. Chlorine is a strong oxidizer, and yet you mix chloroform, which is an organic, with a strong oxidizer. Is that a sensible thing to do? No. You don't want to mix strong, because what are you going to get? You're going to get a fire or potential explosion. And so why the heck would you mix chloroform, an organic, most organics are highly flammable, with chlorine, an oxidizer which is even stronger than O2, right? So automatically some kind of mental alarm bell might click on taking an organic and mixing it with a powerful oxidizer. Maybe I need to be scared. Fear is good. But a lot of people, if the room is dark or if they can't see anything, they aren't afraid, even though they could be very hazardous, right? Fear has that. Like if you're driving on a road and there's a huge drop-off, when it's pitch black, it's so easy. But when it's bright out, it's pretty scary. If you might actually fall off the cliff. But the same thing here, if you don't know, then there's nothing to be afraid of, right? I can just go ahead and mix the organic with the oxidizer and have no problem. And so this is why I asked some of you, not everybody was at the same point, but this is why I asked some of you to tell me a little bit about chloroform, because why the heck are you mixing an organic with an oxidizer like that? Chloroform must not be like your typical organic, right? Must not be. And so that's why I'm asking you, because automatically, hey, this is a no-no. You don't mix organics with oxidizers unless you want a fire or an explosion. Well, chloroform is special. It's different, and so that's why it was okay to mix. This is one of the reasons why I do so much in chemical properties, because this survival instinct hasn't really been developed in a lot of people. In Chem 1B, I used to not spend so much time talking about redox reactions. But in Chem 1B, I had a student that was making up a lab. Did I tell you about this? I don't think so. In the lab, they needed ethanol. And so they were making it up at the same time the other people were doing a lab that required strong acid and permanganate. And so in the waste jug, there was lots of strong acid and lots of permanganate, powerful oxidizer. And so I had two waste jugs, and I told the student, put your waste in this jug. Don't put it in this jug, right? I just told them that. But you know what happened? They poured the ethanol, not into that waste jug, they poured it into the waste jug containing strong acid and permanganate. Ethanol. And so an explosion occurred. But fortunately, the bottle didn't break, but it just went out the top, out of the hole. But they were kind of short, so they were actually inside the hood a little bit, burnt their face and their hair, singed their hair. But they were wearing, the person was wearing goggles, so that protected their eyes, but that was an explosion. And everybody was like, what happened? And it was very loud. And so I know a lot of people, they don't think about this because they don't care. They just mix it together. Everything's okay. But no, something, you see something like this, and does anything trigger? Like you see something like this and you go, wait a minute, For example, if I gave you these three ions, right? Acetates, chlorates, and nitrates are all soluble. Would you group those three in the same category? Yeah, because they're all soluble. But then again, would you group those three, acetates, chlorates, and nitrates? Would you group those three together in terms of chemical behavior? No, definitely not at all, because acetates are totally different than chlorates and nitrates. In fact, acetates and chlorates and nitrates aren't compatible with each other, because acetates are like sodium acetate, or acetic acid, You know, do acetates burn? Would sodium acetate burn? Would acetic acid burn? Does acetic acid burn? Like, for example, you know, it's not going to burn like alcohol, but could you burn acetic acid? What do you think? Like, for example, if somebody eats vinegar, do they get any calories from it, or is it just calorie-free because nothing happens to acetic acid or acetate? Does carbon monoxide burn? Carbon monoxide burns. Is it a good fuel? Not that great. You know, methane's much better. Acetic acid burns. Acetic acid is the fuel. If you were to eat a lot of vinegar, you're going to get calories, right? You're going to get calories. So what happens in the body is, well, let's look. If I took ethanol and combust this, you know, I'm going to form CO2 and H2O and energy. This is chapter 7 stuff. This is, the states matter. So ethanol is a liquid, O2 is a gas. This is not balanced. H2O is a liquid. We get energy. And so I can combust this. You know, when I combust this, eventually I end up with some energy. Or I could actually burn this in the body. If you drink a lot of ethanol, you know, you're going to get a lot of calories because what your body does is it essentially burns it by a series of reactions. So the ethanol, do you know what ethanol is converted into in the body? You know, there's metabolic cycles in the body, and these things get converted into different things. But ethanol starts to get oxidized. Ethanol gets oxidized to acetic acid. And so, you know, ethanol goes to acetic acid, which goes to this, which goes to that, and eventually what's going to happen is you're going to exhale the remnants of ethanol as CO2. And so you're going to get CO2 and H2O, liquid, and you're going to get energy. But when we metabolize it in the body, it undergoes a whole bunch of little steps here. Well, when we burn it in air, does it undergo a whole bunch of little steps? Well, what's that blue stuff in the flame? Is that blue stuff the CO2 or the water, or what is that blue stuff in the flame? Those are intermediate species. And so even when we combust this undergoes a whole bunch of little steps here. But the little steps this undergoes and the little steps this undergoes when we metabolize it are totally different. But the end result is the same. The end result is we end up with CO2, water, and energy. We end up with CO2, water, and energy. And so this is the interesting thing about thermodynamics. Do we get more energy by burning it, or do we get more energy by metabolizing the ethanol? You tell me. The answer is neither of those, because we get the exact same amount of energy. And so the amount of energy by burning it in air versus the amount of energy by metabolizing it in our body is going to be the same, because thermodynamics, this is what we call a state function. A state function is this. A state function only depends on the final and the initial. Since the final and the initial are the same in both of these, then we get the same amount of energy. And so energy, which is the total energy of this process, we have another word for total energy. Do you know what the total energy is also called? Internal energy. And so the internal energy change, and that is the total energy released from this, is exactly the same in both these. That's a state function. Whereas acetate is it's not a great reducer. I mean, vinegar doesn't burn very well, right? Vinegar is acetate with a hydrogen cation. It doesn't burn very well. but it does burn. You know, those are incompatible because nitrate is a oxidizer and chlorate is a oxidizer. And so automatically I see incompatible chemicals there, but we group them together for solubility rules. So anyway, this is part of the process. The part of the learning process is not having to look up everything. Do you want to have to look up the MSDS for everything? No, you want to be able to look at it and get some kind of idea of the reactivity of that chemical. Okay, there's another chemical that we're going to use, and that is MnO2. MnO2 is going to act as a catalyst. A catalyst just speed up the reaction. They aren't consumed in the reaction. And so we add the catalyst. But what about the properties of MnO2? You know, this is called manganese 4 oxide or manganese dioxide. So manganese 4, that's in the +4 oxidation state. That's kind of high, isn't it? And so you might expect this to be a strong oxidizer, huh? How many +4 cations do you know? Not much, right? Lead 4, manganese 4. It's not really a cation though, it's in that oxidation state. We're going to look at the structure of this. And so maybe manganese, this is a powerful oxidizer, huh? What do you think? Well, here maybe some factual knowledge would help. And manganese dioxide is known to geologists as desert varnish. You know, if you go out in the desert and you see this black varnish coating on the rocks, that's manganese 4 oxide. And that is an extremely tough, unreactive material. And so this stuff isn't very reactive. Here. But you can always look it up in the MSDS to see what it's like. So the whole point of this is if nothing registers here, you know, when you look at it, you look at a formula or you look at a chemical, nothing clicks, and then search the MSDS and get more familiar with it. Redox, you know, redox always produces. Redox reactions, you always have to be careful because, you know, some things don't react as cleanly. So, do you know, if I had a mixture of methane and ammonia, let's say I have methane and burn it with ammonia, do you know what you can form? If you combust methane with ammonia, you can form hydrogen cyanide gas. You know, is hydrogen cyanide gas very, very safe? No, so if somebody has a spray bottle of ammonia with ammonia, and you're spraying the flame, is that a smart thing to do? No, because the potential for generating hydrogen cyanide is going to kill you. Right now, when we're talking about toxicity, there's a huge difference between hydrogen cyanide and potassium chloride, even though both are toxic. And so redox, we always do those reactions in the hood if we don't know what's being generated. And even if we know what's being generated, like for example, chlorine's being generated, it says to do it in the hood, and I think everybody did it in the hood, which is the right thing to do. But not everything's going to click. So if you see somebody doing something dangerous, you know, make sure you let them know. You know, maybe they don't know. Maybe they're going to mix some potassium chloride with some, or pour it down the wrong waste container, or do something like that. All right. Well, we're in chapter 7, so let's take a look at this reaction in more detail. And when we take a look at potassium chlorate, in chapter 7, we got to define the system. And the system is going to be one of two things. So how should I define the system here? I'm going to have some potassium chlorate, let's say, and a tiny bit of MnO2. Both of these are solid. How should I define the system? This is called an energy level diagram. We like to work in energy level diagrams because we can see, are we going up in energy or down in energy? What's happening? And so energy level diagram just has an arbitrary y-axis, which is some unit of energy. And we use total energy. The total energy is given the symbol what? U, right? The internal energy. And so we start off with something here, U initial, the initial internal energy or total energy. And then what happens? Then what we do is we heat this up to get it to decompose. And so we add heat to this. Heat. Heat is by the symbol delta here, or we say Q, or energy. Energy is being added to this. And so we're going to heat it up, and then it's going to decompose into KCl, solid, plus 3/2 O2 gas. Nothing happens to MnO2 because at the beginning of the reaction it's MnO2, and by the end of the reaction it's MnO2. So something might have happened, but it gets spit out just the way it was. And so there's no net change to the MnO2. We don't cancel it because it's not just a spectator, it participates, but it's regenerated. So what is our system? Well, the first thing we need to define as far as systems go is our system a what or what? Is our system a what or what? So what do we need to know about our system? Yes, is it an object or reaction? In this case, it's a reaction. And so the system of interest, our system is a reaction, and our system is going to be the KClO3 goes to KCl plus 3/2 O2. And then we're going to have MnO2 in there as well as a catalyst. That's our system. The surroundings will be everything else. Now, a system is a reaction. Reactions have something special associated with them. Whenever our system is a reaction, then what we need is we need the initial temperature. This is going to be at 25 degrees C. And then we heat it up. If we heat it up, it's going to get hot. So it gets very hot. And so what's our final temperature going to be? Oh, we're going to heat it up with a Bunsen burner. This is going to get extremely hot. It's going to get so hot it's going to melt the KClO3. But with state functions, all we care about is not how it gets there. We just care about the initial state and the final. And at the final state, after everything's done, then what's the final resting temperature going to be? Is this going to stay at, probably heat it up to 700 degrees C. Is this going to stay there forever? I don't know what temperature we're going to heat it up to. But for reactions, we know that the final temperature is going to be well, I'm heating it up with a flame, so what is the final temperature going to be? Final temperature is going to be the same as the initial temperature, 25 degrees C. And so what we do is, yes, it's going to get hot, but we're just going to wait until everything calms back down. to room temperature. And so is the KCl and the O2 that's generated going to stay hot forever, or will it cool down enough so I can touch it? It's going to cool down, and the longer I wait for it to cool down, the lower it's going to get. And so what this means is this. Basically, U initial and U final. U initial is equal to the kinetic energy initial plus the potential energy initial. U final is equal to the kinetic energy final plus the potential energy final, because the total energy is the sum of the kinetic energy plus the potential energy. Delta U here is the change. And so did the kinetic energy change? What's delta EK? This is the change in kinetic energy. Did the kinetic energy change? Well, what is kinetic energy? Kinetic energy is temperature. So did the temperature change? No. So did the kinetic energy change? No. There's no change in kinetic energy here. This is 0. The change was in potential energy. That is KClO3 versus KClNO2. There's a difference in the potential energy of these two. O2 being a good oxidizer. Change in potential energy. All right, so our system is a reaction. In reactions and processes, there's never a change in temperature. A process would be like boiling water. When you boil water, you know, the temperature of the water is 100 degrees C, and you convert that water into steam. The steam is at what temperature? It's at 100 degrees C. And so there's never a change in temperature. I mean, there could be, but you know, if you made a change in temperature, then you have to have a combined equation, which complicates things. So we'll just try to keep things simple. In other words, you know, the delta T here is 0 to keep things simple. To keep calcs simple. You know, of course there could be a delta T, but we aren't going to do it. We're going to just wait until everything's cooled back down. Versus an object. You know, an object, if you have an object, you know, there's no chemical change in the object. The object is just going to go a physical change. In other words, if we have an object like KClO3 and we heat it so it doesn't decompose, we'll have cold KClO3 and warm KClO3. And so we heat it up, not hot enough to decompose like this, but just to get warm. Right? So we heat up the KClO3, now it's hot KClO3. And so if we have an object, with an object, the potential energy doesn't change because we have KClO3 here, we have warm KClO3 here. The potential is the same. The difference is in terms of kinetic energy. And so when we have objects, then the potential energy term is 0, the change, and the change is entirely kinetic. We're going to look at this in more detail later, but okay, so our system is a reaction. Now, we have a choice. You know, we could have an open system, closed system, or isolated system. What do you think we're going to go with? Like 99% of the time. Not an open system. In fact, 0% of the time we'll do an open system. Open systems are too messy. 99% of the time you're going to be using a closed system. And so if nothing's specified, we assume this is a closed system. Isolated systems you're going to encounter in the homework. You know, isolated systems aren't really talked about in the book much. In the homework, there are I think two homework assignments. The isolated system that they're going to give you is something called an adiabatic system. And it's going to deal with the adiabatic expansion or adiabatic contraction of a gas versus isothermal. Isothermal would be just a regular closed system. Adiabatic would be an isolated system. So you'll see that later. So this is a closed system. There are two types of closed systems. Tell me what they are. Constant pressure, constant volume. And so here we got a closed system. And so with this closed system, we have two choices. We could have constant pressure or constant volume. Let's take a look at constant volume first. We'll do this as a constant volume closed system. Initially, what we have is we have a mole of KClO3. And so here, the initial volume, a mole of KClO3, well, how much volume does a mole of KClO3 have? Let's take a look at that. Let me turn it off and on. See if that works. Well, so we look at the Wikipedia entry for potassium chlorate here. The molar mass is 122.55 grams. And so a mole of KClO3 is going to be about 123 grams. We got 123 grams. We look at the density. The density of KClO3 is 2.34 grams per cubic centimeter. So let's just go with 2 roughly and 120. So that's about 60 milliliters. And so we have about 60 milliliters of solid KClO3 here. Solid. The rest of this is going to be air. You know, this is closed, and so this is just some fixed volume container. We don't have to have any air. We could just have 60, you know, milliliters, but we'll just have a container like this. All right, when the KClO3 decomposes, it decomposes into KCl, right? Which we looked at the MSDS for KCl. You got to look at the MSDS for the products too, not just the reactants, because you're forming the products. And so we're forming some KCl. Are you very worried about the toxicity of KCl much, or the hazard? No, the KCl is pretty safe. And so the molar mass is 74. And so we're going to form about a mole of KCl, which is about 75 grams of KCl. And it's about 2 grams per cubic centimeter. And so 75 divided by 2 is about 37, 38. And so we're going to go from about 60 milliliters solid to about 38 milliliters of solid. The KCl is less. Are you guys following along so far? All right. Actually, we didn't look at the MSDS for oxygen. Let's look at the MSDS for oxygen. MSDS oxygen. This is a different manufacturer here. This is nice. You know, different manufacturers emphasize different things. Like the hazards was much later in the other MSDS. And so you could pull up different MSDSs and get a much better feel for these. But, you know, oxygen is an oxidant, strongly supports combustion, may react violently with combustible materials. Good. What else do we have? Oxygen. Well, this is good. No known toxicological effects from this product. Violently oxidizes organic material. May react violently with reducing agents. May react violently with combustible materials. Exposure to fire may cause containers to rupture or explode, non-flammable. All known extinguishants can be used. This is more user-friendly MSDS. Again, there are lots of them here. So we could go to this one, Matheson. This gets a health rating of 2. 4 is the worst. Potassium chlorate gets a, what's the health rating on potassium chlorate? Actually, let's go back and look. Well, long-term exposure. Long-term exposure, irritation, cough, chest pain, lung damage. But, you know, unfortunately, we have long-term exposure to oxygen every day, otherwise you're not going to live very long. And so when you read these, you know, you can take them out of context easily. You know, it's going to cause lung damage. Well, anyway, so MSDSs, yeah, sometimes they're helpful, sometimes you really have to analyze it a lot more in depth. All right, so what's the difference? Well, when we're dealing with constant volume, how do we think of the gas part of this? Under constant volume, do we think in terms of Daltons or do we think in terms of Avogadros? We think in terms of Daltons. And so in Daltons, the partial pressure of the gases are additive, right? The volume's fixed. And so we have pressure of air in here initially. Let's make this container. I'm going to make this a 500 milliliter container. Right? 500 milliliters. And now at the end, we don't just have air in here. We still have the air. So we got the pressure of the air. But added to the air, we're going to have another gas. The other gas is going to be O2. And so we got the pressure of the air plus the pressure of the O2. Now this is going to be P total. Over here, the pressure of the air, this is P total because we only had one gas. So this is Dalton's. You know, the partial pressures are additive. Then we got to think. Normally, we're going to generate 1.5 moles of O2. Normally, under normal conditions, 1.5 moles of O2 should occupy what volume? Well, let's say 1 mole. 1 mole of gas occupies what volume? 24.45 liters under normal conditions. We'll just call it 25 liters. And so what we're going to do is we're going to generate 1.5 moles of gas. That's 25 plus half of that is going to be about 38 liters of gas. And so under normal conditions, we should generate 38 liters of gas if we're going to decompose a mole of KClO3. Well, okay, 38 liters, but you know what we're going to do? This is constant volume, so the container is fixed at 500 milliliters. And so now I'm going to compress that 38 liters into this volume that already has air in there. And so this pressure, the pressure of the O2 is going to be very high pressure. Very high pressure. It's going to be very high pressure because of all that oxygen I'm generating. And so we got to make sure that this container is strong enough. And this container, the way it looks like a submarine because it's heavy-walled stainless steel with heavy-duty bolts securing everything, you know. And so this container is very strong. When you're doing constant volume chemistry, you got to make sure the container is strong enough to withstand the pressures, because this is Dalton's, right? Dalton's is the pressure can go up, up, up. Likewise, the pressure can go down, 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 because if we have a gas and we're consuming that gas, then all of a sudden it was this big, now it's shrunk down to this size. And we have an implosion hazard. So we got explosion and implosion hazards. These two boxes were supposed to be the same size, but unfortunately I didn't make them the same size. Let's cut this down a little bit. 500 milliliters. And so we give a special name to constant volume containers. You know what we call this container? Yeah, we call this container a bomb. It's called a bomb because we don't want it to explode. That's the last thing we want to happen. And so the bomb has to be strong enough to withstand the high pressures that are going to be generated because of Dalton's law. Dalton's law, you were just going to keep adding pressures and adding pressures to this, right? When we don't want it to implode, likewise, if we start removing pressure, this can implode. And so we have to use a bomb-style apparatus that's constant volume. The other type of system that we're going to look at is not constant volume, it's constant pressure. And so if I were to do this reaction under constant pressure conditions, what I'd do is I'd have, let's say, a container here, like this. And then I just put a balloon here. And so here I'm going to put my 60 milliliters of solid and plus the air. So yeah, air. When I do it under constant pressure, then I'm going to not use Dalton's. I'm going to think in terms of Avogadro's. And so what I do is this. What's going to happen is, as the O2 is being generated, the container is going to expand. One way to get the container to expand is just put a balloon on the end of this. So let's put a balloon here. And this balloon is going to grow to how big? Well, how many liters of O2 am I going to generate under normal conditions? Pretty soon I'm going to have a additional plus 38 liters of gas. Right? And so the balloon's going to start off small. And so what this says is whatever volume of air I had there initially, what I'm going to do, because this is Avogadro's, is the volume of air plus the volume of O2 that I generated. And the volume of O2 is going to be about 38 liters. This is going to be V total. Now, why do we care whether we do this under constant pressure or constant volume conditions? Why we care is because the energy will be different. Let's say somebody asks you, can you do me a favor? Can you blow up this balloon? You say, sure. And then they tell you, well, I just need it 38 liters big. Would you be happy blowing up a 38-liter balloon? That's huge. You'd probably say, no, you know, I really can't do this because it's too much. Too much. Too much work. Don't you think blowing up a 38-liter balloon is too much work? Yeah, it's way too much work. I wouldn't want to blow that up. Take a long time and probably be pretty exhausted by the end of it. This is just too much work to blow that up. And so, in other words, what has to happen is the system has to go from whatever initial volume it is, call it B initial, to the final volume up here. And so what has to happen is the system had to blow up the balloon, otherwise this reaction wouldn't go. I guess you could cap it here so it wouldn't, but you know, that's not going to work, because the pressure will increase. And so what we got to do is we got to let the balloon expand. So that means this. That means when you're heating this up, not only are you heating it up to decompose the KClO3, this is a redox reaction, but you're also heating it up to, you're giving it energy to blow up the balloon. Versus this, under constant volume, do we have to blow up a balloon, 38-liter balloon? No, so you save yourself a lot of work. If you do this under constant volume, boy, you don't have to blow that up. That's a lot easier. But you're thinking, well, I don't have to blow it up, but I'm generating huge pressure. Well, what is huge pressure? Because generating additional O2 in this, and a gas is mostly empty space, just having more molecules in empty space, is that going to do anything? No, there's going to be more collisions, but is it going to be more work to put another O2 in empty space? No. And so when we do this under constant volume, we don't do any work, because the O2 is just being generated into empty space. And you just have more molecules of O2 in there. A lot more molecules just means more collisions with the wall, higher pressure. But there's no additional work. Whereas if you do this under constant pressure conditions, then you got to blow up this balloon. And so thermodynamics is really focused on energy. And so the amount of energy it takes to do it under constant volume is different than the amount of energy it takes to do it under constant pressure. Which one of these requires more energy to be input from the burner? This one. Constant pressure is going to require more energy input than constant volume. And so this is why this stuff is important, because you know we can do it either under constant pressure or constant volume, and the energies are going to be different. And so we got to keep track of this so we get the right energy calculated. Well, where does this heat come from? Well, this heat is going to be coming from what we call the surroundings. You know, this is going to be externally input energy. And so the system is going to gain this energy, the surroundings is going to lose this. Now, do you know the first law of thermodynamics? The first law of thermodynamics states that energy is conserved. Energy is neither created nor destroyed. Right? There are different ways of expressing the first law of thermodynamics in terms of this. So one way is, if we look at delta U of the universe, delta U of the universe is the total energy of the universe, final, minus the total energy of the universe, initial. Do you know what that equals? The total energy of the universe. Let's say I did that reaction, KClO3 decomposition. Before, what was the total energy of the universe? And after I did that reaction, what's the total energy of the universe? It's zero. The total energy of the universe is fixed. There's no new energy being input. There's no energy being lost. And so any energy that went into this change, into this decomposition, came from somewhere, and that somewhere is the surroundings. And so what we're going to do is we're going to be looking at this. The delta U of the universe is equal to this. It's going to be equal to delta U of the system plus delta U of the surroundings. And in fact, delta U of the system is equal to minus the delta U of the surroundings. Minus does not mean exothermic. Minus just means opposite sign. Opposite sign just means this. If the system loses, the surrounding gains. If the system gains, the surrounding loses. And so we have a sign convention to take care of this. When we look at the system, this is the way we think of energy. The system can exchange energy in terms of heat, the transfer of this kinetic energy. And so we'll have delta U of the system is going to equal the heat that was exchanged with the surroundings. So this is what we call Q of the system. And or work of the system. And so energy is going to be exchanged with the surroundings by heat and work. And so the sign convention is this. Let's take a look at Q of the system in terms of the sign. If Q of the system is greater than 0, then the system gained energy. If the system gained energy, then the surroundings must have lost energy as heat. And so gained energy is heat. That means the Q of the surroundings must be less than 0. And that means the surroundings lost energy as heat. And so typically, when we think about heat, heat can do different things depending on what we're looking at. Does heat always increase temperature? If you heat an object, does it always increase the temperature? No. It won't increase the temperature if a reaction or a process occurs. It will increase the temperature if it is an object. And so, anyway, system gained energy, surroundings lost heat. If Q of the system is less than 0, then the system lost energy and the surroundings gained energy, or lost heat, gained heat. Therefore, another way of thinking about the first law of thermodynamics is this energy is neither created nor destroyed. So it's just transferred. So whatever the system gains or loses is going to be the opposite of the surrounding. So what we say is Q of the system is equal to minus Q of the surroundings. And the minus is just to change the sign, because the surroundings does the opposite of what the system does. We can also have energy exchanged in the form of work. The work would be like blowing up the balloon. Who blew up that 38-liter balloon? Well, the system had to, because the system's volume increased by 38 liters. And so here, when we think about work of the system, if it's less than 0, then the system lost energy doing work. Well, if the system lost energy blowing up that balloon, then wasn't that energy consumed in blowing up the balloon? So when you're done blowing up the balloon, then you've just burned all of that energy, right? Didn't that energy just disappear? Must have just disappeared because we used that energy to blow up the balloon. But the funny thing is the energy didn't disappear. You know where the energy went? Into the surroundings, because all that energy you lost blowing up a 38-liter balloon goes into the surroundings. So the work of the surroundings, well, the surroundings is going to gain energy when the system loses energy. And so we have a gain here. Likewise, let's say the surroundings loses energy. Let's say the surroundings had to blow up the balloon. So the opposite thing happened. Let's say the system got smaller. If the system gets smaller, the surroundings needs to get bigger. If the surroundings needs to get bigger, it's got to blow up the balloon. And so here the system, the surroundings loses energy by blowing up the balloon. That means the system is actually going to gain energy. And so if it costs 400 joules to blow up the balloon, that 400 joules doesn't disappear. That 400 joules just went to the system, oddly enough. All right, so we're going to focus on heat right now, and we'll take a look at heat. Actually, we could come up with this first law here as well. Work of the system is equal to minus work of the surroundings. This is another way of saying the first law. And therefore, delta U of the system is equal to minus, Q of the system plus W of the system. This is also the first law of thermodynamics, saying that energy is neither created nor destroyed. Okay, let's focus on heat now. We're going to do some homework problems here. Well, when we're looking at heat, heat can do two things, right? One thing heat can do is change the temperature. And so when we're looking at heat, Q, we do two things. One, if it's an object, the object can get hot or cold. And heat is going to be related. Heat of the object is equal to the amount of object times C times delta T. Or did heat do anything? When we heated up the KClO3, eventually it went back down to the same temperature. But something happened. And what happened was, in a reaction or process, the heat caused some kind of chemical reaction or chemical change to occur. And so the way we do that is Q of the reaction or process is not equal to amount times C times delta T. This is equal to the amount times, I'm jumping ahead here, it's going to be the amount times delta H. We'll talk about delta H later. But delta H is when we do constant pressure. Or it's equal to the amount times delta U. Delta U is when we do constant volume. So you got to keep track of all these things, right? Constant pressure, constant volume. Do we use delta H? Do we use delta U? Well, we'll learn more about that as we go along. But this is just the intro part. Is it an object or is it a reaction or process? Use these equations. You wouldn't believe how many people try to use this equation for everything. Even when delta T is 0, we plug in 0 there. But it's easy to do, because if you're a little shaky, then, or if you're a lot shaky, then it's very easy to get the equations mixed up. And so let's do some homework problems here. We'll start off easy. So this is thermo, so it's best to start off easy and then get harder, rather than jump to hard like I've been doing. We're going to start off with the easiest possible problem, which will be 1A. 1A, calculate the quantity of heat in kilojoules required to raise the temperature of 9.25 liters of water from 22.0 to 29.4 degrees C. So we'll just focus on heat right now. Later on we'll look at work. But we're going to have 9.25 liters of H2O liquid. And we're going from 22.0 degrees C here up to 9.25 liters of H2O liquid at 29.4 degrees C. And so this is our system. Our system is 9.25 liters of H2O. Is our system an object or a reaction or process? It's an object. And so we have cold object, hot object, or warm object. And so our system is an object. Anyway, this is an energy level diagram. What we got to do is we got to increase the energy of our object here. Are we increasing the kinetic energy, or are we increasing the potential energy, or both? Is this an increase in kinetic energy, or an increase in potential energy, or both? An increase in kinetic energy. Was there any change in potential energy? No. And so the only thing is we're changing the temperature. How are we going to do this? We got to input energy here. Well, we can input the energy in the form of heat or work. Well, we're going to input it in the form of heat, so we're going to add some heat to this. Now the amount of heat, well, this is Q of an object. When we look at Q of an object is equal to the amount times C times delta T. The amount of object we have is 9.25 liters. C, a lot of people have C memorized for water, which isn't that difficult, because to 3 sig figs, it's 4.18 joules per gram degree C. That's over a wide range. To 4 sig figs, this isn't accurate, because the specific heat of water changes a little bit depending on what you or where you are in the temperature range. You know, actually 1 calorie is defined for, I think, 4.5 to 5.5 degrees temperature change. But anyway, this is good 3 sig figs. Times delta T. Delta T is T final, 29.4 degrees C minus T initial, 22.0 degrees C. Units don't work out. Degrees C cancel, but grams and liters don't. And so I need to convert liters into grams. So let's go milliliters first. And then what's the density of water? The density of water to 3 sig figs is 1.00 grams per milliliter. To 4 sig figs, this is no good, but to 3 sig figs, this is the density over a wide temperature range. So now milliliters, liters cancel, grams cancel, degrees C cancels. And we're left with joules. Joules is the amount of heat that we want to add to this. Now, looking at this, how many sig figs are we allowed? There's 3, 3. After we do this 9.25 is 3, 4.18 is 3 sig figs. 29.4, this is going to be 7.4. It's 2 sig figs. 1,000 is infinite sig figs. And 1.0 is 3 sig figs. So it looks like our final answer should have 2 sig figs. But I want you to carry extra here and then round to 2 sig figs there. And so that's how much heat is required to raise the temperature of that object. Okay. All right, the next problem is B. The heat in joules, in kilojoules, sorry, associated with a 33.5 degrees C decrease in temperature in a 5.85 kilogram aluminum bar. So we're decreasing temperature in part B now. We can convert that to kilojoules easily. But in part B, again, we have an object. It's going to be 5.85 kilogram bar of aluminum. So we got 5.85 kilograms of aluminum solid. And that's initial and final, 5.85 kilograms of aluminum solid, final. And the temperature drop here, the delta T is equal to a 33.5. Well, if we're losing temperature, this is going to be minus 33.5 degrees C. We don't know what T initial is. We don't know what T final is. But we know that T initial has got to be greater because delta T is T final minus T initial. Therefore, T initial has got to be greater to have this drop. All right, so what's going to happen is this has got to lose energy because we're going from high energy to low energy. That energy that's lost is going to be lost as heat. Okay, so again, we're looking at an object. And so the Q of this object, which is aluminum, is going to equal amount times C times delta T. The amount is 5.85 kilograms. And what we'll probably do is we'll change this to grams immediately. 1,000 grams per kilogram, so kilograms cancel, that gives me grams of aluminum. The specific heat of aluminum is 0.903 joules per gram degrees C. So the grams cancel. And then we need a degree C to cancel. So this is going to be negative 33.5 degrees C. The negative sign is important because that tells us, is the system losing or system gaining? In this case, system's losing, so Q is less than 0. And so then we calculate. This one, we're allowed 3 sig figs in this particular calculation. And so the calculations are going to get more complex because the calculations, what we're going to do next is see where this heat goes. Well, this heat is going to go into the surroundings. And so what we're going to do is we're going to make the surroundings a simplified version of the rest of the universe, because the surroundings is the entire rest of the universe, which is too much to deal with. But we say, let's say the bulk, or we're just going to assume all this heat gets dumped into water. You know, what's going to happen to the water? You know, if that heat goes into water, the water is going to absorb that energy and the temperature is going to go up. You know, this kind of stuff. Or in the previous example, that heat had to come from somewhere. And so let's see where the heat ends up coming from or going to. And so that's how these calculations are going to get a little bit more complex as we go along. Okay. We'll stop here. Thursday